Okay, once again I welcome you at the uh, for this lecture of remote sensing of soils, and I welcome you at Indian Institute of Remote Sensing, from where I am delivering this lecture. And you can access our website www.irs.gov.in, and for any inquiry you can also access. You can send me the email to the email written here. Before discussing the remote sensing of soils, I will just go a brief over the remote sensing technology at, and what advances are available today. In general, we talk about the geospatial technology, and it is a technology which is integration of three technology. That is, one is the remote sensing satellite, second is the geographic information system, and third is geographic position system, GPS. Remote sensing satellite data, you get the picture of the earth, and you derive the information which you integrate through using GIS. GIS is a computer software where we can have ability to integrate the map in GIS, and GPS helps you to find out the location, precise location of your soil data points or any other object on the earth surface. That's why we call it is geographic position system. If we talk the remote sensing, actually remote sensing data is being used widely for to study the processes, earth surface processes. We are collecting information about that one. It provides us a real time information of natural resources, because remote sensing satellite data are available every fortnight or monthly, or sometimes it is weekly data is available. So you are getting real time information of your resources. And third is the informations you are receiving, that is the reliable information, unbiased information. So these three important characteristics of the remote sensing data, the characteristics of remote sensing data help us to understand the earth surface or understand any object present on the earth, either it is soil, crop, forest, water, anything. When we talk the remote sensing satellite technology, remote sensing satellite, we are having two types of satellites, or in general. One is the satellites we call geostationary satellite, which is the satellites are orbiting at the orbit of 36,000 kilometer, and these are called geostationary satellite. And you are aware that INSAT satellite, which is the weather and telecommunication satellite, comes under this. Second category of satellites, which is orbiting at the orbit of 600 to 800 kilometer, and they are polar orbiting satellites. And the remote sensing satellites, which are these satellites, presently what India have, Resourcesat 1 and 2, Cartosat 1 and 2. So these are the remote sensing satellites, and here today we will discuss the remote sensing satellite. When we talk the remote sensing technology, we talk about the electromagnetic radiation. We know I am going here to discuss you with the optical remote sensing satellite data. In optical remote sensing satellite data, sun is the source of electromagnetic radiation. From sun, radiation is coming to the earth surface, and the radiation which is coming, you can have the range of ultraviolet, visual, infrared, microwave, and radio wave. today we will discuss mainly this visible and infrared radiation, which we call multispectral satellite data or multispectral wavelength region. Microwave remote sensing satellite are the another type of satellite which is we are not studying today, but these satellites are mainly used when your sun is not available, like in Kharif season. When cloudy weather is there, then optical remote sensing satellite data, we are not getting the picture of that one. So in remote sensing, we talk about the it is a electromagnetic radiation spectrum with bands used in remote sensing data. If you see the process, how remote sensing satellite data works, so I can say here that is the sun is the source of energy. From there, the electromagnetic radiation is reaching to your earth object, and your earth object absorb the radiation for photosynthesis, or because of its chemical nature it will absorb some radiation will be reflected, and some radiation will be transmitted. So reflected radiation is captured by remote sensing satellite data, and from there it reflected radiation which is coming from the earth surface recorded by remote sensing satellite data, it again transmitted to the data receiving station in India, which is available at in Hyderabad data receiving station, Shadnagar. There we receive the data, and this data is processed through computer, and we get the remote sensing data. And this data now is processed for preparing various maps or to study the various natural resources. So the question comes, that is, what are the remote sensing satellite data today available from ISRO? So currently you can say that is the resource at 2, which is launched in April 2011. It has 3 camera, LIS 3 camera, 23, LIS 4 camera, and AVIFS camera, and this camera having spatial resolution of different spatial resolution. It means highest spatial resolution is 5.8 meter. It means the satellites can detect the object of 5 meter by 5 meter of size. When it is 23, means 23 meter by 23 meter, we are getting one reflectance value. Now Cartosat 3 remote sensing satellite data, which is the most recent, launched in 2019, which is having in color multispectral, MX means multispectral 1 meter, and panchromatic black and white. Its spatial resolution is 25 centimeter. You can say 25 centimeter by 25 centimeter object of the earth surface, we are getting the reflectance. So you can say it is very detailed informations it provides. We are having, you can say, 1 meter, 5.8 meter, 23.5 meter, 56 meter, and why different cameras are there? To meet the requirement by the different users. We are having microwave remote sensing satellite data also, which is very good for study in the Kharif season when there is a cloudy weather or rains are there. So at that time, that optical remote sensing satellite data resource set 2, Cartosat does not work, or we are not able to get the reflectance because of the cloud cover. But microwave remote sensing radiation, microwave radiation can penetrate cloud and rain and reaches to the earth surface. So we are able to get information in microwave with microwave satellite. We are also going to have in future in in this year end or next year, geoimaging satellite, GISAT, the most important satellites which you will have. You will get everyday remote sensing satellite picture of the Earth surface, and where we are having 6 spectral bands, means 6 lenses are there to capture the image, but spatial resolution is 42 meter. Here resolution is high, resolution is low. Reason is that this satellite is launched at the 20,000 kilometer or so height. So it is geostationary height, therefore resolution will be less, but every day you will get the satellite data. If we see what the foreign remote sensing satellites are available, Landsat 8, which is the from US, Sentinel-1 in microwave, Sentinel-2 in from Europe. These 2 satellites from Europe it is available, and we can get this satellite data freely from the internet. Even Indian remote sensing satellite data, if the resolution is more than 5 meter, then we can get the freely from the ISRO website. These remote sensing satellite data, I am showing you the picture of this Dehradun Valley, and you can see this, it is a Dehradun, and the spatial resolution is helping us to prepare the map at various scale. You see, for village level mapping or micro watershed, we use the 1:10,000 scale. We prepare 1:10,000 scale, and here we can use Cartosat remote sensing satellite data, which is resolution of pan 0.6 meter or 1.8 meter. For LIS4 sensor 5.8 meter, we can prepare map at 1:20,000 scale, which is useful for block level mapping, tehsil or sub watershed. Satellite data we can use of resource set 2. For 50,000 scale mapping or for district level mapping, you can use resource set 2 2A satellite data of LIS3 sensor, which is resolution is 23.5 meter, and state or catchment area 1:250,000 scale. We go for 1:250,000 scale, where we can use AVIPS remote sensing satellite data. So you can see that is the different spatial resolution are available with our remote sensing satellite data, which can be used to prepare map at village level, block level, district level, state level. So as per the requirement of user, you can select the scale, you can select the satellite data, and you can prepare. Simply, this slide shows you how remote sensing satellite capture the data. This is the resource set satellite data, which is having 4 camera. Camera is named as B2, B3, B4, B5. It means B2 means this collect the reflectance in this wavelength region, 0.5 to 0.59 micrometer. In this wavelength region, it collect the reflectance. B5 means it collect the reflectance in 1.55 to 1.70 micrometer. So these are the individual camera which pass the reflectance value between this wavelength region, and this is the satellite moving over that or surface. It capture a large area. For example, LIS3 satellite sensor capture in one scene 141 kilometer by 141 kilometer in one scene, and this data it collect the reflectance, and the reflectance is sent to the receiving stations. From there we get the remote sensing data. This is, you see how the satellite image is generated. So you see that is the we get all 4 bands satellite image, and each band image is black and white. But when we merge this, we make the composite, we make composite in a such a way that your infrared is projected as red color, green is projected as blue color, and red radiation or red band camera image is projected in green color, because we have only 3 primary color, blue, green and red. So we are projecting this one in this fashion, and whatever then you will get the composite image of all 3 images, and we call it is standard false color composite. Actually, when your it is this slide is showing, suppose your radiation is coming from the sun, EMR, electromagnetic radiation, reaches to the earth's surface and interact with the plant, then what will happen? Plant will absorb red radiation for photosynthesis, and it will reflect infrared in large amount because of the cellular structure, chlorophyll content, water content and nutrient content present into the vegetation or leaf cell. So this is the one spectral characteristics of the plant, or you can say the leaf. So here you can see, because of chlorophyll, red radiation is absorbed, so you are getting low reflectance, but in infrared you are getting high reflectance. So there is a contrast, red will be absorbed, infrared will be reflected, and this contrast is very useful in characterizing the vegetation or anything which is having chlorophyll content. So this is the one image from remote sensing data, and you see whatever the red you are getting, it is because of the vegetation or because of chlorophyll content, because as I shown you earlier, infrared is projected as red color. So here red will be absorbed by vegetation and infrared is reflected, so vegetation will appear as a red color. And whatever here you are seeing the greenish or color, it is the fallow land. This is the fallow land. This is the forest. Cropland, this orange color you are getting, this is the cropland. So we can see various features on the Earth's surface very easily from the remote sensing data. You see the 1 meter resolution of Cartosat 3 satellite data. What details you are getting here? You see that is these are the fallow land where there is no crop. But here you can see this one, you are seeing in a regular fashion, these are the orchard, mango orchard. It is clearly you can see even the field boundary bunds are having the vegetation like poplar or eucalyptus plantation, that also you can see that one. So all red color means they are the vegetation, and surface which having no vegetation, so red and infrared and green radiation will be reflected in equal amount almost, so they will appear as a white stone or greenish stone. So the combination of these three radiation will decide what color will appear on the satellite data. But today the satellite data are available with the highest resolution. You can see individual agriculture field also. That's why we are calling Cartosat 3 satellite data we can use for village level mapping, even for individual farmers field. When we want to analyze the remote sensing data, there is basically 2 types of methods we use. One is the visual method, where you can say the manual method. We are seeing the false color composite image. Based on the color, texture, pattern, shape, size, we can identify the object. What is the object is there. Another technique is the computer based technique, machine based digital image processing, where we can enhance the satellite data, its contrast we can enhance, we can do supervised classification or computer based classification of your satellite data, supervised, unsupervised. We can generate the spectral indices, so we can do number of analysis over that one by visual and by computer based digital image processing. So now I just tell you that what are the potential application of remote sensing and GIS in agriculture. So here in blue color it is shown for the soil. We can use it for soil resource mapping, land evolution for land use planning, agroclimatic suitability analysis, mapping of degraded land, monitoring of degradation and desertification, digital terrain analysis, digital soil mapping, soil nutrient mapping. We can use this remote sensing data. Besides that, we can use for the watershed management also. We can use remote sensing data for climate change studies, where we can study the impact of climate change on soil quality, soil erosion, or soil carbon. In agriculture, if you see, we can use the remote sensing for crop mapping, crop yield forecasting, crop disease, drought assessment, crop insurance, precision agriculture, agriculture information system, and many more. So there are various applications of remote sensing data are there today, and you can say today remote sensing data being has been recommended and being widely being used for precision agriculture, because from remote sensing data you can find out where the crop condition is poor, where the soil nutrients are low or soil nutrients are high. So it can give you information about the fertilizer management, and that is the precision agriculture. Means precisely you use your resources to enhance or to optimize your crop production. Now I come to the soil, which is our the topic, and earlier I have gone through in to tell you the basics of remote sensing. That was basically I prepared those who to your brushing your knowledge or brushing with your basics of remote sensing. Now, how we can use remote sensing for soil information? We know what is soil. We say that is soil is a three-dimensional natural body for us. Here you see the three-dimensional natural body, where you are seeing one soil profile, and surface you are seeing the horizons, and subsurface you are seeing the horizons having different composition. And so in the normal soil mapping, we characterize the soils from surface to subsurface, or we can say we study the soil profile, soil horizons. As you know, the soil is made of mineral matter, organic matter, air, and water. And here the right side you picture seeing that is the some soils get degraded. For example, salt affected soils, where the composition of the surface soil is changed. So you know, if the radiation is coming from the sun, and when it interact with the salt affected soils, it will, the amount of reflectance will be different from your normal soil. So in remote sensing we study mainly the reflectance behavior of the object. So reflectance behavior of the soil, if it is normal soil, the reflectance will be different than your problematic soils or soils salt affected or eroded or any other kind of soil. So first, the definition of the soils, you can say soil is a natural three-dimensional body. When we talk about the soil mapping in any other lectures or tomorrow and after day after tomorrow, what we will talk, that is the traditional soil, or we will talk the normal soil mapping, and for that we define soil as a three-dimensional body, and which the properties are resulted from its soil forming factors. These factors were responsible for developing its physico-chemical characteristics of the soils, and in this soil mapping we study the different horizons, various layers. You know, the top horizon, which is the organic horizon, A horizon, B horizon, C horizon, and so these different layers we study. So a soil horizon is a you study the, take the samples horizon wise, and then you characterize. So this is the soil for us, not only the surface material. When we want to characterize the soil, we characterize the soils based on the morphological characteristics, soil depth, soil color, horizon depth, root density, color mottles, consistency of the soils. Physical characteristics: texture, structure, density, porosity, infiltration rate, soil moisture characteristics. Chemical characteristics: pH of the soils, electrical conductivity, carbon, nutrient, CEC, micronutrients, all these characteristics we need to characterize of the soils. So therefore we characterize these characteristics of each soil horizon, and for that one we use the various uh, take the help for measuring the color, soil Munsell color chart. If we know the sand silt clay proportion, then we can characterize the texture of the soil. So in the remote sensing, when you are studying the remote sensing for soil studies, so there is a two things are there. One, we study the conventional soil mapping. When we go for the conventional soil mapping, where, and another is the digital soil mapping. We both describe you. In conventional soil mapping, when we talk about the soil map, then it means that is the conventional soil map, which has been prepared by the interpretation of multispectral remote sensing data, and we characterize the soil up to 2 meter depth and of each horizon. Another is the digital soil mapping, where we characterize the surface characteristics only, not subsurface. Here surface, subsurface both, but in digital soil mapping we characterize mainly the surface characteristics, surface properties of the soil. Here we use the digital techniques, and we are using the hyperspectral remote sensing, multispectral remote sensing. So here you can say that this digital soil mapping is a quantitative analysis, but conventional soil mapping is a qualitative analysis. So so one day our lecture will be on conventional soil mapping, which I will tell you, and at the end I will tell you about the digital soil mapping as well. So when we study with the remote sensing data, so first thing, that remote sensing, the electromagnetic radiation coming from the sun, when it reaches to the earth surface, then we study the reflectance. So reflectance, you see, if you see the vegetation, if you see the vegetation, green color it is shown, in different wavelength region or in different waveband camera, the reflectance will be low and high. So here you can say in visible wavelength the vegetation gives the low reflectance, but in near infrared it gives the high reflectance. But in case of soil, it is always increasing the reflectance. We are not getting very peculiar characteristics. So basically we study the reflectance characteristics, but subsurface reflectance characteristics I cannot get directly from the remote sensing data, because electromagnetic radiation cannot penetrate the soil. It will give only the surface reflectance. And if you want to know about the subsurface characteristics, then remote sensing directly we cannot get, but indirectly how we can get, we will also discuss in third lecture. So your electromagnetic energy is coming into the surface, then it will be absorbed, partly it will be transmitted, and it will be reflected. So reflected radiations we analyze, we see that in which spectral bands how much energy is getting reflected and why it is getting reflected. So it is getting reflected because of the composition of the soil. So it is shown a different soils will give a typical spectral signature, spectra, and this spectral signature of a soil is a very unique. That's why we also call it is signature, as your signature. That is your unique, about the unique for the person. Similarly, spectral signature of different soils are unique, and if they are unique, then you can map those soils directly from the remote sensing data. Here I am showing the soil reflectance. You see this, if the soils B, you see, soils having low organic matter content will give the high reflectance. But the soil A, which is having high organic matter content, which will give the lowest reflectance. But you see the E, soils having high iron oxide. So initially it will have the high reflectance, but after 1.1 micrometer, it will give the low reflectance. So if I take the satellite data in this spectral wavelength region and in this wavelength region, and if the reflectance is becomes opposite, reverse, then I can say it is because of iron oxide or it is because of organic matter. I can identify, and this quantity of reflectance will it is related or associated with the amount of the organic matter content. So I can know if higher the organic matter content, low reflectance, and lower the organic matter, high reflectance. And if I establish the relationship between this reflectance and quantity of organic matter, then I can, establishing this relationship, I can map the organic carbon present in the soil, organic carbon present in surface soils, I can map with the remote sensing data very easily. And not only the organic matter, but other mineral constituents like salt content or nutrient content also can be mapped using reflectance characteristics. Here I have shown you the wavelength region, and in this wavelength region you can map this compound or this composition of the soil, that is organic matter and water mapping. You can use this wavelength region, and for clay mineral mapping, for example kaolinite, montmorillonite, or any clay minerals, you can use this wavelength region 1 to 2.5 micrometer. And carbonate on other minerals, you can use this wavelength region. So you can say that for particular compound, particular wavelength regions are available which can be used for mapping of that one. Here in this graph also I can tell you, that is we are getting here the low reflectance, or you are getting absorbance at 1.5 and 1.9 micrometer. Actually 1.4 and 1.9 micrometer wavelength region, we get the absorbance of the radiation because of water content present into the soil. So it is, you are getting low reflectance because of water content. If you see this graph, sand dunes are giving the high reflectance, laterite soils giving in between, and black soils giving the low reflectance. So I can tell you that in the different kind of soils, they have the unique spectral signature, and that can be helped to map those soils directly from the remote sensing data. Here you are seeing the spectral characteristics of soil moisture, where you are seeing that is, I told you 1.4 and 1.9 micrometer is water absorption band. But as the water in the soil is increasing, you see the top one, it is the dry soil. It is the dry soil giving the high reflectance. But here it is, you are getting the low reflectance because of high moisture content. It is shown that is 32.8% moisture into the soils. As moisture content decreases, reflectance goes increases. So we can make the relationship between reflectance and moisture content also, and sometimes, and in general, we measure the soil temperature and soil moisture content to map the soil moisture. But today, mainly microwave remote sensing is used for mapping of soil moisture content into the soil. Another one, previously I told you the multispectral remote sensing data, where you are having 4 spectral bands or up to 10 spectral bands, we call multispectral. But when we have more than 100 spectral bands or more than 100 spectral regions you collect the reflectance, then it means you are collecting the reflectance in a quite detail. So this will help you to identify the type of salt, type of clay mineral as well, and it is very useful. And so one more technology is coming, that is hyperspectral remote sensing. US has launched one satellite, Hyperion 1, that was having 220 satellites in this 220 spectral bands in this much wavelength region. And we are able to generate a unique spectral signature. So we are able to map clay minerals, soil nutrient, organic carbon, salinity, soil texture, all these things very clearly. And here it is right side, it is shown the spectral characteristics of different clay minerals, different materials you are getting here. So in particular wavelength region, we can identify that material or that composition present into the soils. Today, Italy has launched one satellite, Prisma, which is hyperspectral remote sensing satellites, so that we can use for mapping of the individual composition of the soil. Now the questions comes, can we map soil based on the soil reflectance? You can map the soil if there is a no cover, no vegetation present onto the surface. If on the surface there is a vegetation or crop or forest is there, then you are getting the reflectance of crop and vegetation, not of the soil. So one problem. So take the satellite data when your crop is harvested, generally in alluvial plain in Uttar Pradesh or any region. If you are there, you find out the crop calendar when crop is harvested. So your land will be fallow land. So you select the satellite data of that period. One thing. Another thing is that if soil, I am interested to get the information of surface soil, then we can directly get the reflectance. But in conventional soil map, I am not only interested for the surface, but I am interested for the subsurface soil. For example, here you see, in this, here I don't know which kind of soil is there, because surface reflectance we cannot get. But when I removed that one, you see the soil, underneath soil is like that one. So it means from the surface reflectance alone, I cannot map the soil. So I have indirect approach for that one, and one lecture will be delivered on this topic, how I can map these soils. I am showing you one satellite image. You see at 2 point, the color of the on the satellite image are same, but it means similar reflectance are there, but similar reflectance does not mean similar soil, because here and here soils are different, because the parent material is different, so therefore soil will be different. So even when there is a vegetation cover, when we want to study subsurface, then we go for indirect. But certainly when you want to study the surface characteristics of the soil, mainly for the degraded lands, where the soil properties changed of the surface soil, that we can easily map with the remote sensing satellite data. Here I am showing you, can we map degraded lands using remote sensing data? You know that in country 120 million, 120.4 million hectare is our land is degraded, and you can see our 86% agricultural land is degraded and 14% forest land is degraded. And because of water erosion, 70% of degradation or 80% degradation is mainly because of your erosion, either water or wind erosion. So, and this degradation affect the surface soil. For example, salt affected, you will get the salt on the surface. So you will get a unique spectral characteristics. Eroded soils, where top layer is removed, so you will get also the peculiar reflectance characteristics. So I can easily map erosion, chemical degradation means salt affected soils, and physical degradation, which is 1% area in the country is there. It is because of compaction of the soils. Soils become compact. So because of compaction also soils give high reflectance. So degraded land soils we can easily map from the remote sensing data. How? I will show you. Actually, how erosion take place? You see on the ground, rains are occurring, and because of rain, rainwater will be absorbed by the soil due to its water holding capacity, and the remaining water, and some water will be evaporated by evaporation and transpiration. So water is lost, and the remaining water flow from the surface, and which cause the soil erosion. So you see on the surface, this is the paddy field, and the soil water is moving from the surface as a surface runoff and causing erosion. This is the different type of erosion: splash erosion, sheet erosion, rill erosion, gully erosion. And you are getting the different photographs. I have shown you how erosion you are getting. Can be these eroded lands be can map from the remote sensing data? Yes, by visual analysis. Just by on satellite remote sensing data we can see. You know, for visual analysis, where you need your eyes to interpret it. And we know there is a four type of mainly erosion classes: sheet erosion, or you can say slight erosion, moderate erosion, gully erosion, severe erosion, and very severe erosion, that is dense gully erosion. And how they appear on the remote sensing data? You see, this is the one hill, Shivalik Hills. Here you see the very white reflectance, and this area you are seeing. Actually, soil is washed out from the surface. In erosion, topsoil is removed. So in topsoils you have high amount of organic matter, high amount of clay content that will be washed, and sand will be left, or coarser material will be left. So the coarser material will give you high reflectance, and because of high reflectance in all spectral bands, it will appear whitish tone, whitish color on the satellite image. So seeing the intensity of whiteness, you can interpret it as a slight erosion or moderate erosion. Here you can see the pattern, that is white is there, but here more white is, here less white is. But here if you see, you are seeing the irregular channels. They are the like stream. These are the basically gullies, gully formation. So you can see the gully formation very well on the satellite data, and you can interpret it. This is very severe erosion, this is severe erosion, less gully here as compared to this area. So remote sensing data you can interpret it directly to map the various erosion classes, and which we need to for preparing land use plan. Here you see the salt affected soils. We know that is the salt affected soils are saline soils, sodic soils, and saline sodic soils. And saline soils having high salt concentration, and saline sodic soils also have high salt concentration. And if you see the reflectance, strongly saline sodic soils give the highest reflectance. And you see the normal soils you will get first the low reflectance, and then in this spectral wavelength region the reflectance will be high. But you see here, strongly and moderately saline soils are giving high reflectance in all spectral bands. In this wavelength region, this wavelength region, and this wavelength region, you are getting the highest reflectance. Therefore, on satellite data, it will appear as a white tone. This is the salt affected soils filled picture is there. You are seeing the white tone. And when I see the satellite data of that area, it appears like that one. So I can easily map the salt affected soils. But you know, the salinity and water logging lies together. They are the twin problem. Jahan salt affected soils honge, at the same place you will get the waterlogged area also. So you see the water logging in the agriculture field, and it is appearing a bluish tone on the satellite data. Here is the bluish tone, the salt waterlogged area. So I can easily map this one, but I need to take the satellite data of proper time when the salt are in maximum amount on the surface. So generally in April-May month, all the salts from the soils comes to the surface. And at that time, the reflectance of the soils will be entirely different from the normal soils. So I can easily map normal soils and salt affected soils. I can use the salt affected soils for monitoring purpose also, because here you see the picture is showing the salt affected soils waterlogging in Rohtak district of Haryana. So you can see here whitish tone salt affected soils, and this picture is showing the image was classified in 90, and yellow the salt affected soils is shown in a yellow color in 1990 May month. It is a image classification by computer. You can give the computer the training that this is the salt affected soils, and the computer will classify where are the salt affected soils. So yellow color is showing the salt affected soils. But after 10 years, when we have taken the satellite data in 2000, same month, we find that this yellow color has increased, means salt affected soils has increased. Here more white, more yellowish, you see from here compared to this one. So large area under salt affected, and here in 90 there was no salinity, but after 10 years here you are also getting salt affected soils. So remote sensing data, you can monitor in which direction, which area, and how much degradation has increased or degradation has decreased, that we can do very well with your remote sensing satellite data. That's why we say remote sensing data are very useful for monitoring of your resources, monitoring of your degradation. So here I have given a brief about you about how remote sensing satellite data can help us to study the soils. So today in this lecture I have shown you the reflectance characteristics of the soils, how the composition is affecting the reflectance, and then I have told you that is the surface characteristics of the soils we can easily map from the remote sensing satellite data. So I have shown you the eroded land mappings or erosion mapping, and another is the salt affected soils. So, but I have not discussed about mapping of soils up to 2 meter depth, or which we call the normal soils or conventional soil mapping. So conventional soil mapping I will discuss in detail on 6th March, that is why to map soils and how to map soils. Tomorrow you will have a lecture on soil forming factors and processes, which is very important to understand the remote sensing of soil mapping. Here you will be told how soil has been formed and how to characterize the soil. Then this lecture, next lecture I will discuss, that is how you can classify the soils using soil taxonomy. So then I will come to this remote sensing of soil mapping, which will be there. I will tell you about the conventional soil mapping methods, where to take the soil samples, and other questions will be addressed in this one. For your information, I recommend you to read this a booklet of 100 pages, Earth Observation for Soil Resource Assessment. Here I have given the website address. You can download the PDF copy of this booklet, and which will help you to understand our lectures, and it is briefly described in this as well. So thank you for joining today's lectures, and thank you for joining this outreach program started on remote sensing of soils from today. Thank you all.